Good afternoon, everyone. How are you all today? Feel like we haven't talked in a couple of days. So, I don't know about you, but it's a really warm day here in Sydney, and I'm having a great time. I put my jumper on this morning. I was like instinctually put on my jumper, and then I was like, damn, it's really warm. So, it's been a great day. Um, Lots of people chatting about Comp 1521 being confusing. I'm not going to lie, that's the stuff I have the least interest in personally. So I'm thrilled that I'm not doing that subject. But, I've never been a big low level person anyway. So I hope you do have fun with it though. More fun than I would have. That course didn't really exist when I was studying. They had a different course, which I think was probably 1521 is probably better than that course. Well, more relevant, I should say. But um, just as a bit of a preface for today, um, the two topics we're going to be chatting about today are minimum spanning trees and shortest path. So we're going to be trying to figure out, given a graph, what is the minimum spanning tree of that graph, and then given a graph with a couple of nodes, how do we find the shortest path between those nodes? What's the shortest path between those nodes? We're also going to try and chat about assignment 1 at the end. So assignment 1 was released on Monday. Assignment 2, assignment 2, assignment 2, assignment 2. And the main things that I want to chat about today are part 1 and part 2, ideally. And in fact, what we're covering today in part 1, what we're covering today with shortest path should make part 1 a lot clearer. And then part 2 is actually really quite easy to understand. And then next week we'll try and talk about part 3. This assignment's not due for like 3 whole weeks, so we will talk about it then. Good luck with assignment 1, by the way. I mean, what's the lecture attendance at? It's at 61, relatively low. So I hope you're doing all right with that. I've heard the help sessions are really busy. If your help sessions are really busy, just remember the teaching staff do their best to adapt to it. We put extra people on when we can. If you're in a massive queue of like 50 people, just don't sit there thinking I'm waiting for 2 hours. Like, go do something else for an hour and a half. It's like, it just takes time. And, I know this might not be particularly comforting for people, but, when I did my entire undergraduate degree, which was not that long ago, it's only like 2012 to 2016, we never had help sessions at all, really. And most of those people still managed to figure out how to survive. I'm not saying, everyone did great, but it's like if you're ever feeling stressed and you're feeling like you're not getting support, I guess all I'd say is like, there are people just like you who backed themselves and, really just said, okay, I can figure this out, I can debug it. And they got through it, and I'm seeing this with a lot of students generally in the course is like, back yourself to debug things. If you have a problem with your code, I don't really mind what your competency level is. Most people are capable of trying to narrow down the scope of a problem. So, I believe in your own abilities, and I think you should too. And I'm not just saying that. It's true. So let's get stuck into minimum spanning trees. This is a fun little topic. I like it. We get to learn about two little algorithms. It's a little bit like when we did graph algorithms and we did Hamiltonian and Euler stuff. We're going to be doing a very similar thing here. And it's actually really easy. These algorithms are quite straightforward to get your head around. We're not going to be doing any coding on this one. That's just a decision that's been made in the course. But we need efficient ways to generate minimum spanning trees from a graph. Okay, and again, like, what are the applications of minimum spanning trees? Anytime you have a complex network of things and you want to figure out how to join every vertex together, which is a minimum spanning tree, then you need to look at algorithms like this. And I talked about this last week, but I just want to contrast this again. If you have a graph, right, like if you have a graph like this one here, on Tuesday we talked about NP completeness and the difficulty of algorithms. And we kind of said that there are certain algorithms that are easy, like finding an Euler path or an Euler circuit, or I've already forgotten, or doing, like a binary search or something like this. And then we said there are some algorithms that are hard, as in they grow exponentially. When we talk about connecting vertices in graphs, just as a reminder, the two main ways that we talk about it are either by Hamiltonian path, which is a linear path through a graph that connects everything, and that's a really hard problem to solve, right? Like, I just tried to solve it then and I couldn't figure it out, so maybe I'll go a different way, or, it's hard. It's a lot of brute force, and it's just a hard problem. Minimum spanning trees are not a hard problem. They're not super efficient solutions, but it's actually very easy to find a minimum spanning tree when you're able to not have to form a linear path with things, right? Like, that's a minimum spanning tree there. These problems are a lot easier, and that's the ones that we're talking about. So last week was on Hamiltonian paths. This one's on minimum spanning trees, and it's a lot easier. There are two algorithms we'll be talking about in relation to this. Firstly, just on some general definitions to get your head around stuff. When we refer to a spanning tree of a graph, it's actually just it's a tree that's a subset of a graph that connects all vertices and contains no cycles. If it didn't connect all the vertices, it wouldn't be spanning. If it contained cycles, it would be a tree. It would not be a tree, sorry. And it also has to be a connected subgraph. So I think that's an important point, because if you had, say, a tree like this one, a graph like this one, someone might argue that this is a spanning tree here, because it is a tree, a disjoint tree, or a disjoint graph with no cycles in it. This is not a spanning tree, because while it does touch all the vertices, and whilst it does also have no cycles in it, it isn't connected. And that connectedness is a really, big deal. I mentioned before applications, electrical grids, networks, often things where you want to minimize the edge weights between stuff, but there's no real sense of like order through things. So if you're trying to connect, say, pipes might be a good example, or any kind of grid really. The water doesn't flow around in a linear path between houses, it just goes outwards. And your job is to minimize the amount of pipes, for instance. So that's the gist of where the purpose of this matters. So a quick bit of an example on what the definitions were here, are that if we have an original graph like this with 5 nodes and 6 edges, and we want to find a spanning tree, well, a spanning tree again is any connected subgraph that has no cycles that connects all vertices, right? Like 1, 2, 3, 4, 5, like that. A minimum spanning tree is a form of spanning tree where the edge weights are minimal. Basically, the sum of the edge weights in this tree there is no spanning tree that has a lower sum of edge weights. That's the gist of that. So spanning trees are really easy to find. In fact, you could find a spanning tree in probably a very fast, very quick algorithm, because you just have to connect vertices together. So how do we find minimal spanning trees? Well, a very expensive way to do it would just be to generate all possible spanning trees in the graph that could be applied to the graph, and then we could calculate the total edge weights, find the minimums, because there could be multiple minimum spanning trees, right? So you go and literally generate every single permutation, and then you stack them all up in terms of sum of their edge weights, and there you go. That's it. You found the right one. Now, the reason this is expensive, and if you didn't kind of figure this out from the last lecture on P and MP stuff, generally speaking, anytime you are dealing with permutations and combinations is when you'll start to see these things go crazy. So when we're like generate all the possibilities, that's usually where things start to get into the hard category of algorithm. However, we don't want to do that. We actually just want to find, we have two algorithms that can actually help us find this in a much simpler time frame, a much shorter time frame. So the first of these two algorithms is called Kruskal's algorithm. The second one is called Prim's. We're going to be talking about Kruskal's first. This algorithm is very straightforward. The idea is that you have a graph, say like this, and you start with, let me find a weighted graph for you. Something interesting. You have a graph like this, and what you do is you start off with an empty minimal spanning tree. Now, basically all that means is that, we haven't started. That's just a benign start state. Then what you do is you go and you get all the edge weights here, and you put them in order. So, I could label these, but if you look at all these edge weights, we have a 2, we have a 2, we have a 3, a 3, a 3, a 3, a 4, a 7, a 7, an 8. Oh, 7, 7, 7, 8, 9. I think that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh god, I've missed one. But you get the gist of this, right? You can basically stack all the edges up. Now, if you have an array of edges implementation, you can just sort those edges by the weight. If you have a adjacency list, you could go through all of the lines and pull out all the edges. If you have an adjacency matrix, you could pull them all out of the adjacency matrix and get them into a list. But the point is you basically get all the edges in the graph into a list, and then we're going to start ticking through them. We're going to start saying, all right, I want to try this one and try that one like that. Now what you do is you basically start filling in these lines, and you're building let's look at the real language. You consider all the edges in the graph in increasing weight order, right? So we go this direction. So we start here and we go down. And we add an edge to our minimal spanning tree if it does not form a cycle. So at the start, our minimal spanning tree is empty. It's just nothing in it. So we first take, say, our 2 edge, and we color it in. We say this is now part of our minimal spanning tree. And we keep doing this for all these numbers unless we run into a cycle. So the next one I'm going to do is another 2. So I'm going to then color this in. So we're building our minimal spanning tree like this. And then I have a 3. There's 2 9s. Thank you. That's good. So then I have a 3, and I'll color a 3 in. Like, it doesn't matter which 3, really. Can't draw. So I color that 3 in. Great. There's another 3. I color this one in. Still no cycles. So now what I've got is I've got a graph that has no cycles but is disconnected. It will connect itself in the end, just by virtue of how the algorithm works. I then look at another 3 here. Okay, so that's colored in. I then look at another 3 here. Great. Still no cycles. And then I look at a 4, like here. Great, still no cycles, gotten really lucky. And then I look at a 7. I try and add this one, but you see now we've created a cycle. So I can't add that. And then so that one's no good. And then I try this one here, and we've created a cycle. So that one's also no good. And then I look at this one here, and we've created a cycle. So that one's no good. And then I add the 8, and I've, again created a cycle. Now, obviously, we would have actually probably stopped by now because all the vertices are connected. But you kind of go through that process, adding edges in order, in increasing order, skipping any that form a cycle until you've connected all the nodes in the graph, which we've done here because, A, C, F, G, D, E, H, B, they're all connected. Okay. Very straightforward algorithm, isn't it? Pretty cool. Thank you, Kruskal. Someone said that earlier. Who said that one? Autumnal says, thanks, Kruskal. That's how I feel as well. And you repeat that until v minus 1 edges are added. Now, again, I just kept going with this one, but if we have 1, 2, 3, 4, 5, 6, 7 nodes, then we're only ever going to add 6 edges. So you could have actually stopped this earlier. You wouldn't have kept going, which is good. So that's a bit of an insight, which might be helpful. This is another visual demonstration of this. So if we have our original graph on the top left here, after step 1, we're going to add the lowest edge weight, which is 1, right? Then we're going to add the next lowest edge weight, which is 2. And then what's the next lowest one? 3. So we add 3. What's the next lowest one? 4. We try to add 4. but it forms a cycle in the minimal spanning tree, so we don't add it. Then we add the next one, which is 5. Now, after we've added 5, we now have 4 edges for a graph of 5 nodes, and therefore we're done. So super straightforward there. That's all there is to it. It's quite chill. Does anyone have any questions about this before we move on to Prim stuff? Is it expensive? Well, let's keep going. There's actually 2 more slides. I think I jumped the gun on the questions, but yeah. So Alex says, how do we cover how to detect cycles? We're definitely going to talk about that. So, I mean, firstly, this is a pretty straightforward algorithm here, which is like, okay, well, you create an empty minimal spanning tree, which is basically a graph. You sort all the edges, and then you go through the edges in sorted order. You try and add an edge to your minimal spanning tree. If it forms a cycle, you remove it. And then once you have enough edges, you quit. Okay, so this pseudocode, I'm hoping, compared to other pseudocodes we've seen in the course, is quite straightforward. Probably the only interesting thing here is that the process is to add an edge to the MST, then check if it has a cycle, or a cyle, as I have misspelled here, but it should be cycle. That's the process. Now, in terms of the complexity, people are asking, how do we do cycle checking? How expensive is this? This algorithm's time complexity is a really interesting topic. You'll see a few different, I guess, answers for this online, or at least I've seen. And the way you have to think about it is that you're going to have there's 3 parts to this, right? You have to sort the list of edges. Now, what's the cost of sorting the list of edges? Well, so far we know it's e squared, because we know that things like a bubble sort are e squared. But next week we're going to be talking about how there's actually algorithms that'll be quicker than that. So we can actually say that sorting the edges is an e times log e operation. The second thing we have to do is we have to iterate through all the edges. Yeah, we have to iterate through all the edges, but we only have to iterate at v minus 1 times, right? So we want to iterate through all the edges until we reach the end. So that's ov minus 1, which is ov. Yeah. So that's because if you have a graph of 8 nodes, you're going to have to do at least kind of 8 checks of the edges. Obviously more, like that could technically blow out to OE, but there's a generalization here. And then the next one is that each time you actually iterate through the sorted edges and you try and add it to the MST, you have to do a cycle check. Okay, now the cycle check complexity we have down here, check for cycles, we've just got down as OV squared. There are different ways you could do this. Like a simple one is a depth first search. So like a depth first search is an easy way to detect cycles, because if you have a graph like this one, and I wanted to check if there's any cycles in this graph, all I have to do is keep track of a visited set. And I start here, so I add A to my visited set. I go here, I add C to my visited set. I go here, I add F to my visited set. I go here, and suddenly I'm back at something I've already visited, right? So you can adapt a DFS to work really quickly for something like this. There are faster ways, no doubt. Off the top of my head, I'm not sure. Demjin says, for checking a cycle, could you just check if the vertices are connected? If the vertices are connected, are already in the MST. No, because like in this case here, you could, like, I mean, with Kruskal, technically, like, these two could already be connected. So if you add something here, it's already in the MST, but you don't know if it has a cycle or not. So you would have to actually search it for the cycle. But yeah, if we assume for a second here that checking for cycles is v squared and that iterating through all the edges is OV, and we look at sorting the edges as E log E, what you end up with as the general complexity of this is something like E log E. Now, I did some searching around trying to find a bit more explanation on this, because I remember the first time I saw this, I thought, wait, why is it O log E? Why are we just ignoring the cost of the cycle check, right? Um, just before I get into that, Wally, can you help me understand? Because I just explained how to check for cycles. So what? Just give me a bit of a sense of what more we'd want to elaborate on that topic, because it's actually just a DFS where we keep a visited list. So if we're doing a DFS and we keep a visited list, which we actually already do, because like the iterative DFS that we actually both DFSs that we gave actually had cycle checking in them. Because if you have a DFS without cycle checking, it just goes forever, right? Because you could just get caught in loops as the DFS just keeps exploring in a loop. So a normal DFS actually has cycle checking in it. It's just that, if you were to go back to, say, our graph traversal stuff, where is it? DFS. If you were to go back here and look at, say, this algorithm where we set visited W to be equal to V, it's like, just as part of this algorithm, if you ever had a point where you're trying to add the children and one of the children has been visited, yeah, it's you basically just be like bootstrapping on top of this to check if you've like, because here what we're doing is we're only exploring a graph if we haven't visited it. So if we attempt to visit something we've already visited, then you know that there's a cycle. Because in theory, if you run a depth first search on a tree, I mean that's all a binary search is, right? It's just a big kind of tree search. If you run a DFS on a tree, you should never need a visited list, right? Because the visited list will never find something. You'll never try and explore something you visited before, because the tree doesn't have loops. So you could actually just honestly manipulate the DFS algorithm really trivially. I'm just reading some more. Okay, sure. So that's yeah. So in terms of the complexity, I was quite interested in finding a way to explain to you about why the complexity we teach in this course says that Kruskal's algorithm is E log E complexity. The answer, I was looking around on the internet for some kind of interesting explanations of stuff, and this article probably was the most interesting to me, which was essentially talking about. So, firstly, when you see this online, you are likely to see a lot of E log E or E log V. So, for instance, if I just go Kruskal's algorithm complexity, and we go Googling this around, difference between prims and, will it be here? Complexity? Yeah, so they'll talk here. So Kruskal's algorithm time complexity is E log V. And we've kind of said in the lecture slides that it's E log E. And I've seen different ones on top of that, but an explanation I really like here is that, Kruskal, where is it? Kruskal's algorithm's E log E. Okay, now that's a sorting thing. If you're like, why is it log? It's the cost of sorting. Okay, like the cost of sorting E edges is E log E. You'll take my word on that until next week. They say you could also say that it's E log V, right? Which V is going to be smaller than E, right? Like if you're trying to connect a graph, there's going to be there's going to be roughly the same number of edges as vertices, but there could be a lot more edges in the worst case, right? So what they're saying is that E is definitely less than V times V. That's just like a property of the graph, because you can't have, for E edges, E is always going to be smaller than the square of the vertices. Okay, so log E, we can say therefore that log E is less than 2 log V. So we're just doing a little bit of math manipulation here, right? In terms of we're just kind of taking the log of both sides here, if everyone remembers high school math, because I sure don't, so I'm going to lean on you here. It's like, so if we take the log of both sides here, we end up saying that log e is definitely less than 2 log v, right? So that's essentially where the derivation comes from, as to why some people say O log v, because they think that, log of e is less than 2 log v, and then the coefficient kind of disappears. But it doesn't really matter specifically here, because like log v and log e are all relatively in line. I mean, there's some other discussion about it here and whatnot. But the point is, I'm just trying to explain to you why we're telling you e log e. You'll see this somewhere on the internet. This is what's been taught in the course previously. If we go find it on Wikipedia, I'm sure we'll see. Let's see what we find on Wikipedia. Kruskal's algorithm. Is it up the top here? Complexity. Thus the total time is e log e, which equals e log v. So that's kind of the short answer. So if you see e log v, like, don't stress out. It's like it's kind of the same thing. You can go and read the link I gave. You can go and read this to kind of understand how those two things are roughly equivalent. There's the question of like, so Waleed asked the question. So why do we ignore O of v squared? That's a good question. I probably don't have a great answer for you off the top of my head. Something I haven't thought about too extensively. I'm not even sure if that's an accurate I mean, the thing is, it depends how you do the cycle checks too. Because like if you're DFSing a tree, that is already a minimal spanning tree, then the DFS will in theory only have to do v steps, right? Like sorry about the construction noise. It's like if you have a minimal spanning tree like this, and then you add another edge in like that, the DFS only has to go 1, 2, 3, 4, 5, 6. Like it doesn't have that many possibilities it can go, because it's basically operating on a tree with potentially one cycle. So I don't actually think a DFS is v squared. Some of these things are carryovers from previous lectures, and I'm not actually 100% sure why that was written there, or I probably missed something. But what I'd say is a DFS in the context of trying to check for cycles in a minimal spanning tree is pretty quick. Yeah, so I mean, in this case, I think that I do think that a DFS on a minimal spanning tree would be basically OV. And then you'd have to do OV exactly V times, which is where we get V squared. Now it's all coming back to me. That's right. So yeah, it's like we have to do V iterations over sorted edges. And a DFS is going to be V for us. So what that ends up being for us then is like the overall complexity of this. You could write down as like e log e plus v squared, and then I'm guessing there would be some maths around this that says that e log e is greater than v squared, which just escapes me off the top of my head, but I'm certain there's a relationship here that basically says this is a lower coefficient. Yeah, I'm not too sure. Like, I'm not going to lie about that. I'm not too sure why that particular part is disregarded from the complexity. I'm sure it makes sense, though, because I remember making sense of it previously. But we end up with O log E or O log V as well in the end. Graph things are really tricky because, in reality, too, if you were actually doing this on a real graph, you also wouldn't just generalize O and V together. In terms of like, some people have graphs where each vertice has at most, for every vertice there's at most 3 edges associated with it. So you can nearly guarantee that V equals 3e. You could nearly guarantee that E equals 3v. And in the case where you're certain that E is equal to 3v at most, E and V become very similar values as well. So like in a case where you have a very sparse graph with very few edges, v relative to e is actually quite large. But in a graph where, say, for instance, v is actually approaching v squared, right? So v approaches v squared, which is like a dense graph, like a complete graph, then you can kind of imagine the above equation up here as like, this is like v squared, that plus 2. And what do we know? V squared times log v squared plus v squared is just going to be that. So like this actually, like getting rid of the v squared component for a graph that's not sparse makes total sense, because the v becomes irrelevant. Like you got 10 vertices and 100 100 edges. So oh yeah, Namit's just said that anyway on the chat. Which I guess, and I mean, I like having discussions like this, because I guess this is where my confusion comes from. Because if you have a graph, for instance, again, like just to really reiterate this point, so starting again to summarize, we know that Kruskal's algorithm is e log e or e log v. You can find that via any quick Google. We also know, trying to derive this ourselves, that sorting is o log e log e, and that the actual cost of iterating through all the vertices and doing a DFS is about ov squared. So in theory, we get left with o log e plus v squared. Now, how do we know if we should get rid of that v component? Well, we know that in an extremely sparse graph, which is basically already a tree, that the number of edges will be v minus 1 vertices, right? Because you have 10 vertices and 9 edges, connecting them barely. Or alternatively, you could have edges as v minus 1 squared. I can't remember what it is, but let's just simplify this and say v squared and v, to keep it really simple and get rid of like constant components. It's like, okay, well, in the first case here, the actual complexity you're left with then could be equivalent to e log e plus e squared, in which case the algorithm is actually approaching e squared in terms of its complexity. In this case here, you're dealing with v squared log v squared plus v squared, which actually just approaches v squared. Well, sorry, v squared log v squared, which is actually the same as e log e. That's the extent of my understanding on it. And if I have missed a small detail there, I am sorry about that. But the point is that if you're always doing Kruskal on dense graphs, as in ones that have many more edges than there are vertices, then e log e makes perfect sense. And you can just write that out mathematically like I've done here. On a graph where you only have like as many edges as vertices, I'm not 100% sure on if that still holds true. But go read on it. It's really interesting. I mean, the thing about time complexity too is like understanding time complexity is not memorizing a bunch of tables we give you. It's reasoning about algorithms and data structures. It's looking at something like this and trying to make sense of how it works. Right? It's writing it out like that, asking questions, because none of this is set in stone. Like a lot of this is very conceptual, very generalized. You can get into lots of situations where it well, we're going to learn about a couple of those next week, for instance. I was going to think of an example, but I realized that's something we haven't done as opposed to something we have done. Now, moving on, and let's just round out this minimum spanning tree topic. We have another algorithm called Prim's algorithm. And Prim's algorithm is just another approach for computing a minimal spanning tree. The process we follow with this one is that we start from a vertex in an empty minimal spanning tree. We actually start at a point, right? We're not starting at the lowest edge. We're just starting at a random vertex. It doesn't matter what it is. We then look at all the edges surrounding that vertex, and we choose one that won't form a cycle and is the minimal edge weight of all such edges that we have access to. Now, this one is a little slightly less straightforward, but still really simple. What I'll do here is I will we'll talk through this example, and then maybe we'll trace one out. So with Prims, you start at a vertex like 0. So up here you can see in the top left, we're starting right here. Now, 0 has 3 edges around it. Yeah? It has 3, 2, and 8. Now what Prim's algorithm says is that you're always going to select the lowest edge, the edge with the lowest weight, or at least try to. So I select 2. That's what I do. Okay, so now our minimal spanning tree is made up of 0 and 2. It's made up of this little mini graph here with 0 and 2 and an edge between it. So the next edge we explore comes from a list of all adjacent edges in that entire graph. Okay, so what I want to stress here is it's not one of 2's edges that we have to pick from. It's one of all of the edges immediately around the graph. You got to imagine that this, like a Prim's algorithm, is like you have a graph and you start off your minimal spanning tree by making a mini graph, and then it just leaks out in every direction, like water if you were to pour it on, some concrete with holes in it, and it's always going to head down the path of least resistance. Okay, so what's happening here is that this little mini graph here, we can now fill in the 8, the 3, the 4, or the 1, right? The water's got to, or the 5. It's got to go somewhere, and it's going to go the smallest one. So it's going to pick the 1. So the set we're picking from here is all of those edges. So we pick the 1, and now this is our minimal spanning tree between 0, 2, and 3. Okay? Because we've added 3, the edges we can pick from are still the same. It's just that we now have 7 added here as well because of the 3. So it is always the adjacent components, right? And then the next time we do the third step, we say, okay, what's the smallest edge out of 3, 4, 5, 7, and 8? Well, it's 3, so we pick 3 here. Okay, great. Now that we've added 1 to our minimal spanning tree, the 6 is an edge that we can explore too, like this. And then we try and add the smallest edge here, which is 4, but we can't add 4 because it forms a cycle. We can't add 5 because we can add 5. We can add 5. That's what we're doing next. We can add 5. So we add 5, and then there's your minimal spanning tree. And similar to Kruskal's algorithm, we stop the algorithm once we have got all the vertices connected. Like once we've actually connected v minus 1 edges, because this graph has 5 vertices. So once we connect 4 edges, everything is great. Now, let me take you through one more example of this, and in fact, maybe I'll use our original graph here, if I can find it online again. How's everyone doing, by the way? I've had a really busy week. Feeling miserable this week. Should have done more in Flex Week. So, at least the term's nearly over. Sort of. It's week 7. We only have 6 lectures left after today. How crazy is that? Trimesters. Wild. One of them is just a revision lecture. Yeah, lockdown sucks, doesn't it? Yeah, what do people struggle the most with lockdown? Trying to think. I'm very lucky. I'm very lucky that I have a job and that job isn't affected. So I miss family. Yeah. No gym. Actually, a couple of my close friends say the same thing. They feel really kind of cramped up inside with the gym. You've never been to an in-person lecture? Yeah, these things are really sad, aren't they? Just like people who've, I guess, never been to uni. It's like a whole other world. Locked indoors, family and social interaction. Yeah, it's really weird because I live in a share house and I don't talk to anyone in my share house. Like literally, I don't talk to them. And when they're like, "Oh, one person from a household can go shopping once a day," I'm like, "Do I have to talk to them now?" Yeah, being locked out of the country is just wild. But I'm really bringing out the sad mood. I'm sorry. Um, yeah, I mean it's quite a shame that everyone's feeling this way. I think at least we know it's temporal, um, and hopefully Australia can get people vaccinated soon, both for those that live here and those trying to get in. So, um, I don't know. I mean, if nothing else, if you're ever feeling weird, just remember you can exercise with people too, and like you can exercise with people like friends as long as they live within 19. They have to be like at most 19 kilometers in a line of sight from you, right? like 20. So, you know, just I have friends that do that. They're like, oh, I'm kind of lonely, so they go out, they go to a park like 8 kilometers away, and a friend lives like within 8 kilometers of that park, and they just go for a walk for an hour and socially distance, and that's technically outdoor exercise and stuff. So, go read the rules. There's a few things you can do that keep you sane. So, anyway, back to Prim's algorithm. Far more context switch again. So, just to really step through this algorithm. So, what happens here is that I start on a vertex A, like this one here. And then all of the candidate edges, I'll call them candidate edges because they're edges we can explore, are all of the edges, all the neighbors of the nodes in our minimal spanning tree. So A here is now our minimal spanning tree. And it has 2 candidate edges, which are C and F. Okay? So that means that when I do my next step, I have to pick one of those 2 edges. And I'm going to pick 4 because it's lower. So I always pick the lower edge. So there's the next edge. So now my minimal spanning tree has these 2 items in it. Now I have 4 candidate edges, which is C to F, C to G, C to D, and A to F. Right? So it's literally all the edges surrounding everything in my minimal spanning tree. I look at these. The smallest edge weight is 2. So I take that one. There we go. There's my 2. And now my minimal spanning tree has 3 elements in it. Now, if we go back to the original algorithm, one of the important points here that actually simplifies the cycle checking is that when you choose an edge, not in the minimal spanning tree, to add to it, you pick an edge that connects a vertex in the minimal spanning tree to a vertex not in the minimal spanning tree. Okay? So what that means is you don't actually need to do cycle checking, because if you tried to, say, connect 7 here, the rule is that one side needs to be in the tree, one side needs to be out. So therefore you know you can't connect 7. There's no cycle checking you have to do. So that lack of cycle checking is probably one benefit of this algorithm. But if I just keep going with it quickly, we look at our 3... Oh, sorry, there's another candidate edge now, which is the 8 here. So we look at our 3, 7, 8, and 9. We know we're going to pick the 3. Okay, that expands our minimal spanning tree. We pick another couple of candidate edges. We've got 3, 7, 8, 7, 9. Well, we can't add this 7. This one's a no-go anymore. And we have a 3, 7, 8, and 9. Well, we're going to add that 3 because that's the smallest weight of all the candidate edges. This is our minimal spanning tree growing like this. Now we look at what the candidates are. We're going to pick the 2 because it's the smallest number. Great. Now all of our candidates are this. So, and we know that we can't do these anymore because both sides of those edges are in the tree already. And then we pick a 3 because the 3 is the smallest of 3, 7, and 9. And then we get left with 3 final candidate edges, which is 3, 7, and 9. And we pick the last smallest candidate edge, which is this one. And there's your minimal spanning tree. Easy. Great. And you do it till you find v minus 1 edges, till you've filled in v minus 1 edges. Now, the algorithm for this is probably, I mean, it looks slightly weirder, but, you know, at least there's no cycle checking. Because like with Kruskals, there was like a casual line here that's like, oh, just check if there's no cycles. And it's like, well, that's not trivial. Whereas this algorithm doesn't have any massive delegated steps to it. So you create an empty graph, which is your minimal spanning tree. You add a random vertex to it, say the first vertex. You get all of the unused edges in your minimal spanning tree. And then whilst you still have more vertices to connect, because you know you have to connect all the vertices, so you know when you actually finish the graph, what you do is you find an edge, start, target, weight, in the list of unused edges. By the way, when I said candidate edges, that's what we mean here by unused edges. So it's the unused candidate edges. And we want to find an edge out of those candidate edges that is connected. The one side is connected to the MST. The other side is not connected to the MST. So this is that equivalent of cycle checking that I mentioned before, where when we're looking at candidate edges, which are all the green ones, we don't care about ones where both sides of the edge are already in the MST. So that's what this line here is saying. It's saying that one side can be in MST and the other side can't be. That's a requirement of the edges we're interested in. The other requirement, which helps you find an edge that suits, is you need to make sure that the weight of the edge you're looking for is the minimum weight of all such candidate edges. Yeah, so Waleed's right that technically here unused edges refers to all the edges in the graph, and this check here is actually what like susses out the candidate edges. So if I maybe relate that a little bit clearer to what we were drawing before, it's like this is an empty graph, an MST. This is when I draw my first red circle around the starting point. This is just a list of all the edges in the graph. This says let's keep going through this algorithm until we have connected all the edges. And then what this one's saying is I want from all the edges in the graph only the candidate edges, which are the green ones, and I only want the green candidate edge that has the minimum weight. And there's my edge. We connect that edge to the MST, we add the new node to our list of we connect the new edge and add it to our MST, play around with some sets and blah blah blah. So it's don't be kind of scared by the little symbols and stuff and the end things. This is the kind of thing you might find on a Wikipedia page. It's actually very digestible. The notation here could be confusing, but the actual logic is relatively, like, you could teach a child how to do this, right? Pretty easily. Yeah. In terms of the complexity of Prim's algorithm, if we try and understand it, we have v iterations of the outer loop. Okay, that means that because the MST has v vertices in it, we have to do v loops of this edge finding. And then in each iteration, which is essentially like selecting an edge, to find the minimum weighted edge, the complexity we're looking at here is v times e overall. So let me spell this out maybe a little bit clearer. So you always in these minimum spanning tree algorithms have to do v iterations because there's v vertices. So for each vertice you have to do a loop, and then each loop you have to look through the set of edges to find out what's the most appropriate edge. So therefore, the overall complexity of Prim's algorithm, a simple Prim's algorithm, is v times e. Okay, it's not e log e or anything like that. It's just v times e. Because you got v vertices, and each vertice you have to go check all the edges that exist, in the worst case. Naturally, that's a slight overestimate, but that's what it is. On the other hand, if you use a priority queue, which is a data structure we haven't talked about yet, it's actually only v log e. Because getting the right value from a priority queue is quicker than getting a value just out of a list of edges, right? Because a list is, you're going to have to go through every item in the list. Now, we can use a priority queue, and I'll just explain, see if I can find a little GIF for you. This wasn't really something I intended to spend a ton of time on. I hope I can find something for you quickly. Otherwise, I might have to improv. No. So, a priority queue in computing is a... Oh, it says my chat's disconnected. That's weird. Let me just refresh the page. Okay, there we go. Seems okay. Yeah, so a priority queue is like, we understand what a queue is, right? It's this big data structure where we have like, 1, 2, 3, 4, 5, like that. And you insert numbers in this direction, you pull them out in this direction. A priority queue is a structure whereby it's essentially a sorted queue where it can be sorted by anything. But let's say like a normal queue, if you want to insert the numbers 1, 5, 4, 2, 3 like this, then in a normal queue they get kind of inserted like this, right? 1, 5, 4, 2, 3. What a priority queue does is upon insert, it actually makes sure that your numbers are sorted to some rule. So in this case, if I inserted 1, it would go here. If I inserted 5, it would go here. If I inserted a 4 next, it would shift this 5 along and put the 4 here. If I then inserted a 2, it would shift this 5 along and the 4 along and insert a 2. And then if I tried to insert a 3 last, it would shift this 5 along and shift this 4 along, which would be 3. So the idea then is that what a priority queue does is it ensures that when you are pulling from the queue, you're essentially kind of guaranteed to get exactly what you need. But inserting into the queue requires a bit of effort. Now, naturally, yeah, so Gorb's saying it's super easy with a linked list. That's correct. A priority queue would be a linked list implementation because, or some, nah. Yeah, we can talk about that later, but it's like, with a normal queue or a list, whatever, it's normally a list. With a normal list here, which we've talked about as with a set of edges, if you have 5 edges, you have to iterate through each edge to find the smallest one. So that's E steps, and that's why this one is V time. This one is V times E because the finding the minimum one is OE. But with a priority queue, the actual finding the minimum is instant because it's always at the front. The inserting into it though is a log E operation. I'm not really here today to talk about priority queues, but you know, you could imagine if you have a structure that's, think of it like a random access list or some kind of array where you could binary search it for the right spot. You can start to kind of understand like why it could be log E, for instance. The implementation of this is not really something that's scoped in for today, but the main point here is like it's OV times E if you were to just use really standard things. Like if I just say quickly implement this, it would probably be V times E, but if you use a different type of data structure, then it becomes O of V times log E. So that E turns into log E with a different kind of data structure. If you want to learn more about the difference between these two algorithms, you can read up on them here. This is just a Geeks for Geeks site that I think is kind of simple. It gives you one of these comparison tables. There's a lot of things in computer science that you can use this site for. The main things that I think to point out here, besides the complexities, you know, I mean, look at this. This is quite funny, right? Like, the Prim's has a algorithm complexity of O of V squared, right? So these are just, we've said this here is OV times E, and clearly what they're saying here is that they're generalizing E as being V, which, you know, isn't the worst idea in the world because it depends a bit on the implementation, right? But like, you're not going to always iterate through every edge in the graph as part of Prims, are you? So like, if someone was to be like, well, every time I did my exploration before, there was probably roughly V edges, which is pretty true. Like, that's what happened with us. Like, we had 10 nodes, or say 8 nodes, and every time we like added another node, there was like, I don't know, there wasn't like hundreds of edges. So slight different nuances in how you'd express time complexity here. Though I think the main thing to point out is that Kruskal's algorithm can work on disconnected graphs because it isn't quite a minimal spanning tree because it's not fully connected. But like, you remember how Kruskal's just kind of picks edges randomly? What that means is that Kruskal's will work on a disconnected graph, whereas Prim's won't, because Prim starts at a point and tries to like leach out in a direction. So if it comes against the edge of a subgraph, then it just can't traverse any further. It gets stuck. Whereas Kruskal's can do that. Prim's algorithm is generally better for dense graphs. So dense graphs are where you have tons and tons and tons of edges per vertice. That's as you approach a complete graph. And then Kruskal's is better for sparse graphs, which is where you uh, where you have not many edges, basically. Cool. Anyway, that's pretty much it on that. Can you leave some feedback? That would be great. You can pause the video and leave some feedback. Really appreciate it.